Please welcome up to the stage Michael Johnson from Caltrans. He's the VP here for the Western Bridge Preservation Partnership. I don't think he needs really much for an introduction. I think many of us here know all the work that Mike's been doing through Caltrans, through preservation, in all the realms for bridge management. So please welcome to the stage Mike Johnson.
Thank you. This presentation is going to be a little bit different twist on preservation than we've seen to date, or at least through this conference. This was first given 2 years ago internally in Caltrans, and the presentation was specifically designed for bridge designers and bridge construction inspectors. And it was meant to be a feedback loop, if you will, from the inspection side to our design and construction side on things that we were seeing in the field. And so I thought I would present it here today. I know probably most of you aren't designers, but I'm hoping that you'll see this presentation and you will go back to your respective DOTs and schedule your own meetings to talk to your own designers about things that you're seeing that they could do that would help preservation. So there's a couple parts. It's work that was started a number of years ago. In fact, John Hooks, I'm going to credit for the first few slides, did some of the preliminary work for TRB, and I've just been building on it. So here goes. Let's see how it goes. So when you think about bridge preservation, we normally will focus on the material selection, design, construction, and preservation techniques that are going to extend the service life of bridge components or the bridge itself. And like I said, I'm going to kind of focus on the design construction side, but not exclusively. And what really got me interested in this topic area was a couple of questions. One, what is the full service life for a bridge? So you'll hear talk about a 75-year life, a 100-year life, and my role as TRB is to really kind of step back on a kind of higher level and look at this, not so much from a product and material perspective, but from an overall approach. And I didn't want to run past this idea of what is an acceptable service life. Okay, I actually saw a lot of similarities to the presentation on the joints and how everybody's got a different idea of what an acceptable service life is. So that leads to the next question. Well, what causes bridges to no longer provide service? I think we're really pretty weak at quantifying this. And it's something I'm trying to raise awareness on, so hopefully we can make some progress. And then, what strategies can extend the service life? So when I first started asking these questions, it was just convenient that John Hooks, I don't know if is John in the room anywhere? Oh, he's way in the back, he's hiding. John was working on long-term bridge and had access to the entire country's NBI data set for a 20-year period. And so I went to John and I said, hey, can you go in and look for instances where bridges are in the NBI and then the next year they're not? And identify all those bridges that came out of the NBI and then go back to the last year they were reported and give me some information about them. In other words, what was going on with that bridge its last year in service? And so this is John's work here. But I wanted to represent it because it's really good. For the bridges that John looked at in this nationwide sample over 20 years, the average age of bridges that were replaced were not quite as old as you might think. In fact, 72% of all bridges were replaced in 70 years or less. But you could see there's bridges being replaced at 20, 30, 40, 50 years of age. So when someone asks the question, well, what is an acceptable service life? There's really not one answer for that. But a significant number of bridges in this country over the last 20 years are not making it to 70 years. So I said, okay, John, well, what's going on with the condition of those bridges in their last year in the NBI? And so, when we look at, these stack columns are breaking out the deck super substructure, structure evaluation, and waterway adequacy NBI ratings for these bridges in their last year of service. And so what you see is that, we talk about preservation being a huge problem for decks, but of all the bridges that were replaced, this was over 20,000 bridges, only about a quarter of them had deck problems. Okay, so it didn't quite jive with what we were thinking in terms of deck preservation. It didn't appear as though deck condition was driving replacement all that often. And likewise, superstructure and substructure weren't necessarily driving all the replacements. So I said, well, what about some of the other NBI items? So we looked at load capacity. And when you look at all the bridges that got replaced, a lot of them that are getting replaced have very low load capacity, which kind of makes sense. They're not serving the function that we put them in place for any longer. So 33% of the bridges had a load capacity that were below current standards. So that's a pretty decent amount. So you might say, well, load capacity might be one of those drivers. Then we looked at things like deck geometry, structure evaluation, waterway adequacy, clearances. And the one that kind of jumped out was the deck geometry, in that had more affirmative responses in terms of these 21,000 bridges where the deck geometry rating wasn't real good. Okay, so that starts to point towards functional issues being a pretty big driver of bridge replacements. And you can see the others, waterway, we talk a lot about scour, but waterway is hydraulic capacity. That's not really driving. Clearances aren't driving a ton of them, but that deck geometry was a big one. So one of the things, let me go back here for a minute. One of the things that John found in his work was that the NBI isn't really set up to understand why bridges come out of service. You have to infer from the data, and in some cases, a bridge might have 2 or 3 of these things simultaneously. So it's really difficult to tell. So I took that and I said, okay, well, in California, we have the records that we can go back and we can understand exactly why every bridge was replaced. And so I had my staff go in and look at every bridge that had been replaced in the prior 10-year period when we did this analysis. And what came back was that about 41%, by far the lion's share, were replaced because of functional deficiencies. Another 14%, shown in red up here, right here, were done along with highway improvement projects. In other words, we were doing some improvement and the bridge kind of went along with that highway improvement. So it's possible as much as 55% of all of our replacements were being driven by functional issues, not condition or load or others. But we certainly did see condition coming in at 17%. Scour was in here. We would replace some bridges for seismic reasons, so there were some vulnerabilities in there. But that's what the breakdown was, and it kind of mirrored what John found when he looked nationally. And this is looking at project records, and reading the planning justifications for the replacements of bridges. So I had a lot of confidence in this data being the actual cause of the replacement. So what we found was, when we looked at our bridges, the average age in California at replacement over this 10-year period was 52 years. So we're not talking about a 75-year life and certainly not a 100-year life. Our reality is we've been replacing bridges on average at 52. The oldest was 92 and the youngest was 21 years. So we had a pretty broad range, but overall we should be expecting, based on our history, about a 50-plus year life. Of the bridges in California that were replaced, 61 of them that got replaced in this 10-year period, or 32%, were structurally deficient at the time they were replaced. 31 were functionally obsolete, but 36% were neither structurally deficient or functionally obsolete when they were replaced. So that doesn't appear to be a functional issue or a condition issue that was driving that replacement. This is kind of an interesting one because there's some guidance given in the back of the coding guide about how bridges grow in length. And what we found was bridges that got replaced, the bridge that replaced the old bridge was basically the exact same length as the one that was there before. So across our entire inventory, there was like a 0.6 foot, or basically zero change in the length of the bridge. But the width of the bridges, on average, increased over 10 feet. So that told me something. That means that if the bridges on average are being widened by 10 feet, that's generally a lane. So it makes me again think that maybe functional issues are behind a lot of these bridge replacements. So that's what was our study. What I'm hoping is that maybe some of you will see this and be in a position where you could go back to your own DOTs and start asking these same questions, because I'm really interested on a national level to try to understand what's really driving replacements. Because when we think about preservation, we don't want to assume we know what we're trying to preserve for, if that makes sense. And so this is really taking a pause and looking at this question. So from that, I'm going to give you a compilation from my experience of things that I've seen that we could do to improve bridge service life, in hopes to get that 52 years a little higher. So the first area is decks, because decks are where a lot of money goes. I put them first. And really the whole name of the game here is to control bridge deck reinforcing corrosion. That's what it's all about. So there's probably a number of ways to tackle this, but I'll tell you what I would recommend. First and foremost, build a good bridge. So use proper curing strategies when you go to cure your bridge, because if you don't, you're going to get cracks right from construction, and those cracks cause pathways for water and salts to get into your rebar and start corrosion. In California, we've gone to standardized use of fibers in all of our bridge decks to minimize early age deck cracking. This was really a product of a lot of people's work and a lot of study within Caltrans, but I've seen firsthand that putting fiber in bridge deck concrete pretty much eliminates cracking. I mean, it's really significant how much it reduces cracking. So the thinking is, if we can eliminate the pathways for water to get to our rebar, we're going to slow down the corrosion process. Design decks with monolithic overlays that are placed after cure and prior to opening. Caltrans doesn't do this right now. We just cast it all at one time. But there are some states, I think Utah is one, that will do a subsequent, in effect, a manageable course wearing surface that you're putting on top that you can take off and remove and replace, and you never get into that underlying deck. And I think that's a really good practice. It's not one that we use. Evaluate corrosion resistant reinforcing. I said in harsh climates, I mean possibly in any climate. There's lots of options from epoxy coated bars to galvanized bars right back here to stainless bars to carbon fiber bars and others. So look at those as possibly being a good life cycle cost investment. And then when cracks develop, and I didn't say if, I said when they develop in your deck, seal them or overlay them quickly. Okay, cut off those pathways for water to get in there. So if you could do all of this, you would probably get bridge decks that would perform pretty well. Again, I did this initially internally, but I use this as an example. So this bridge was built in 2001, and in 2009, we had already treated it with a methacrylate treatment, which is a deck seal. So that means we had to identify the need for that seal probably 2 years before 2009. So built in 2001, by 2007, we're already sealing the bridge deck. And that's what the bridge deck looked like. Now, this was a slab bridge. None of those cracks go through to the bottom. They were all surface cracks, probably from improper curing techniques. Okay, so let's talk about geometrics and function. And this is one of my big mantras. If you ever go to TRB, come to bridge preservation, I talk about designing bridges that are adaptable for future needs. And I think this is one area where we could really, really improve a lot. So I showed you that most bridges, or the average bridge, is wider than the one that it replaced. That means, you know, are we replacing them because we're putting designs out that can't be widened? That's a question, and I think that the answer will vary from one DOT to the next. But I would encourage people to think about designing so that they can widen, so that if function is your issue, you can add another girder, you can add a couple girders, and you could keep the rest of the bridge in place. This is a big one. So if you widen, will you still have enough vertical clearance underneath? A lot of times you don't, because you have a crown and a cross slope, and as you go wider, you start cutting into your underclearance. So if you're going to do this and plan for a future widening, make sure the elevation of your bridge is high enough so that you have adequate clearance once you do that widening. Rail safety standards, they change all the time. I mean, in my career, I think I've seen 4 or 5 crash test standards for rail. The thing is that most of the changes require the overhangs of the bridges to be strengthened, or a lot of them do. And so when you think about your deck overhang, it's probably not the area you want to economize, because you know that the rail standards will change over the life of that bridge. And if you put a little more rebar in up front, you might not have to do some really special kind of design to accommodate the moments from the new rail standards. Again, load capacity, we ought to look to how we can design bridges so that the load capacity can be increased. So here's some good examples. I say progressive design. The bridge on the left is in San Diego County. It goes over a deep canyon, and the designer had the forethought on this bridge to design the substructure so that it can accommodate another box in between the two that are there. So if we need more capacity, this is an Interstate 8 in California. If you needed more capacity at this location, all you have to do is put an extension of your abutments and put a new superstructure in on the existing substructure. It's already designed for the load. Everything's ready to go. You don't have to get back into this canyon that's pretty difficult to work in. Likewise, the one on the right, a little bit different configuration, but the bent caps were designed from the beginning to be wider than the existing bridge. So if we need to widen this bridge, we take off a rail, we extend the superstructure out over the existing substructure. We don't have to get back in the lake. Okay, those are really progressive designs. This is the kind of thing I'm talking about in terms of an adaptable design. Okay, another area that is a problem sometimes, well, let's just back up to say steel in general. So from my experience, we either have corrosion, fatigue, or impact. And those are the 3 ways that I've seen that steel superstructures don't serve their full life. Okay, but I'm not going to talk about coating systems. I think that's a pretty well documented thing. If you don't maintain your coating systems, your girders, floor beams, stringers, they're going to corrode, and eventually you're probably going to have to do either major rehab or replacement. So I'm a huge proponent of coating systems and keeping your coating systems intact. But steel fatigue's a little different issue because it doesn't show up for a while. Typically 25 to 40 years before you're going to see fatigue start manifesting itself. So if you're going to minimize steel fatigue, how do you do that? And what are the things that to avoid? So this is one of those things that's pretty easy to do. As a designer, you can increase your girder depth beyond the minimum to meet your load or deflection criteria. You can increase web thicknesses beyond the minimum, especially if you're on high skews. High skews are notoriously problematic for fatigue. So if you put a little bit more web thickness, a little bit more girder depth, you quiet the deflections down on the bridge, you're not going to have as big a fatigue problem. Life extension. Limit the deflection. Okay, I mentioned that. Bracing details on steel bridges are absolutely critical. How you brace, and for a lot of designers, I think these are secondary considerations. The bracing between the girder webs is what I'm talking about. Bracing details are usually the source, the connections for them, of almost all fatigue cracks. Not all, but a good number of them are initiated from bracing details. So I did a lot of study on this concept of balancing stiffness from one side of the web to the other, and I'm going to show you some pictures in a minute of what I mean. If you have unbalanced stiffness, as you look at the cross-section of your bridge from one side of your web plate to the other, there's a high probability you're going to get a fatigue crack. This is why they say don't have staggered cross frames, because you have unbalanced stiffness. But there's other scenarios. And the last thing is really tightly enforce welding specifications. Most cracks start in poor welds. If you're not watching the welds, cracks are going to be more prevalent. So here's an example here of a detail that's unbalanced. If you look at this girder line here, you've got sway bracing and a diaphragm or a cross frame here, and on the other side you only have a cross frame. When this girder gets loaded and it deflects down, it gets pulled to the stiff side a little bit. When it gets pulled to the stiff side, it causes incredible stresses on the back side of the heavy stiffness here. The result of that is cross frames that break like this, or like this, or like this. This bridge had probably 50 broken cross frames, and every single one of them was on the back side of a stiff-sided web. Here's another bridge. Notice sway bracing here, no sway bracing in this bay. Guess what? About 75 of these gusset plates fully fractured on the backside. This bridge, we strain gauged up the ones that hadn't broken, and we were getting like 10,000 PSI in these secondary members. Huge stresses developing on the backside. Same phenomena. This girder deflects down, it gets pulled very, very slightly towards the left side of the screen, and it causes huge stresses on the opposite side of the web. In this case, you're lucky it broke the gusset plate. I said, well, this is good because we can replace the gusset plate. A lot of times this actually will move the stiffener and you'll get your crack in the web of your girder. So don't do this detail, okay? Don't do it. It doesn't perform well long term. Okay, so what else can we do? Generally speaking, as engineers, I think we're always taught to economize on design, economize on rebar, economize on the depth of our girder, the pounds of steel. The pounds of rebar are a small little fraction in the cost of building a bridge. The size of your girder is a small cost in the overall cost of a bridge. So if you're going to go with a web that's an 1/8 inch thicker, you're not talking about adding 10% to the cost of the bridge, but you may be adding 20% to the life of the bridge by doing it. So to get to this frame of mind of really life cycle cost thinking, that if I economize and I go right to the design minimums, my bridge might not last as long as it would if I went a little bit bigger. In my own personal experience, I have seen lightweight concrete decks that are okay, but the vast majority of them are not. So I don't like lightweight concrete for that reason, because I don't see the durability. In California, we are on a mission, and Tony will attest to this, to eradicate aluminum joint seal assemblies off our state highway system. They are a dangerous problem because they fatigue out very fast and very easily, And as Tony mentioned a number of times, they have a tendency to fly up into people's engines and other things that can cause really serious accidents. So we stay away from those. If you're in a seismically active state, I do not recommend the use of viscous dampers unless you absolutely have to put them in, because we have a history of them leaking in our state. So again, think about things like widening. How would I widen? What's going to happen in the future? Because it's not about just designing for the number of lanes today, the traffic volumes today. It's about thinking about the life of that bridge. So this is a Vincent Thomas Bridge. This is what we call a damper diaper. That's supposed to be funny. Our maintenance guys came up with this term damper diaper because when the dampers leak, they leak hydraulic fluid, and this happens to be over a parking lot, and so you start dripping hydraulic fluid onto cars, and they don't like it. So we put a diaper on it to catch all the fluid. This is a rubber damper diaper, okay, because it's made out of rubber, but it does the same thing. It keeps the fluid from leaking. The fact that we had to make these things in maintenance is an indication that we have this problem pretty frequently. I could have put probably 50 other pictures like this of aluminum assemblies. This happens all the time. I think Tony showed some of these too, probably different bridges. If we have any kind of issue with aluminum assembly, we just rip it out and replace it. We don't even mess around with it because we've had too many accidents result from them. This bridge I showed you earlier because of this detail here, which isn't good. This bridge also has lightweight concrete. And beyond that, this bridge is on a pretty good size skew. Each of the girders was designed with a different moment of inertia. Every girder is different. So when we look at this bridge, it deflects like crazy because it's lightly designed. The lightweight concrete deck can't handle those deflections. The superstructure has details that really don't perform well in a high deflection environment. So consequently, this bridge, which is about $800 or $900 million replacement, has a lifespan now of about 40 years. So we lost 12 years off our average by economizing on design. So think about how much 12 years of this bridge's life is worth. I mean, when you think about it, you're only going 4/5 of the bridge's life, and you're an $800 million bridge. So if you could have done things differently and bought that extra 10 or 12 years, then you would be saving a lot of money. Okay, and that's the way we got to think about these things. Design loads over time from 1910, you don't see any going down. Okay? It's reasonable to expect that your bridge is going to experience greater load demand in the future than it has at the time you designed it. So think about that. Think about how you can strengthen the bridge. We're building a high-speed rail in California right now. A lot of the designers are coming over from Japan and China to do the design work. Their standard is to put additional post-tensioning ducts that are blanks in every girder. And they're like, we do this everywhere. That's their practice. It costs almost nothing, but it gives you the ability to add another track if you want to down the road. Pretty nice idea. So think about ideas like that. Here's a good one. If a bridge is going to last 100 years, you would design for the vehicle in the upper right. And now we're asking it to handle a vehicle in the middle, all the way across the screen. This is the permit truck in California. It's 54,000 pounds, space every 18 feet for 15 axles. I mean, there's no way a bridge that was designed for this old truck is going to handle this modern truck. So if we can't adapt our bridge to handle more load, it's going to be replaced prematurely. So expect loads are going to increase. What can you do? Tighten up your shear stirrup spacing beyond the quarter points and hold them uniform whenever possible. Don't economize on shear stirrups. You're not saving that much money. You cause just incredible grief and analysis. And as the loads change, those points start moving out, and now all of a sudden you're in an under-reinforced area of a reinforced concrete girder. So tighten them up and keep them tight. It's not going to cost you much more. Don't use temperature steel to resist vehicle design live loads. Okay, leave the temperature steel solely for temperature. Design the rebar to carry the live load. This is another good one. We have designers that in the past would do bar cutoffs to economize. So we're going to cut a bar off early. Now you add more load, and all of a sudden the moment envelope's a lot bigger, and you went past the bar cutoff, your superstructure, your deck's no good. You're not saving that much money doing the bar cutoffs. It's probably costing you more to figure out where to cut them off than to just run them continuously. Increase your deck thickness. Okay, the decks that don't move as much perform a lot better long term. They don't crack as fast. Their life cycle, my own opinion is that life cycle costs make it worth it. So, you know, if you need a 6-inch deck and you made a 7-inch deck, great. Leave the extra inch up top for more cover, even better. Design them to be strengthened and widened, frankly. Okay, here's another area that, I don't know if this is a service life thing, but it is a life cycle issue. This is a really good design. This is an access opening into a box girder. The nice thing here is that we didn't cut it in after the bridge was designed and cut up all the rebar. All the rebar gets bent around, and you get a nice opening that's fully reinforced. Every box girder bridge should have an opening in every bay, period. Don't accept anything less. This is not going to cost you that much that if you have to go in after the fact and you start ripping your box girder soffits apart and cutting bars up, you're going to wish you had done this. This bridge on the right has a catwalk that was put in 40 plus years after construction. The bridge, it's a deck truss. It was put in place for a lake that was supposed to be that the dam never got built. It's way, way up in the air. It's way too deep. An underbridge inspection truck cannot reach the bottom chord, and it's fracture critical. So how do you do a fracture critical inspection on this bridge? This catwalk here was designed so that from the elevation, you can't even see it. It has one cable and a flat expanded metal decking that is in line with the bottom chord. It's invisible. It's really almost invisible, particularly from the ground. And they were worried about the aesthetics of this bridge. But now we can actually go out and do a thorough fracture critical inspection of this bridge from a catwalk, and they can also maintain it and repair it from that same catwalk. Here's another good one. We have a lot of sound walls, particularly down where Tony lives in Southern California. A lot of times they forget to put doors in them to get to the bridge abutments, which are on the other side of the sound walls. Well, if you have a seismic event, this really, really slows down your response time, because getting around, you might have to go 4 or 5 miles up the road and then figure out how to come back to see the abutment, and you got to do that on 2 sides of the highway. So anytime you have a sound wall in front of an abutment, there should be a doorway that allows access through. Here's my favorite damper again. This one's a beauty though. When it was installed in construction, the port to refill it is right up here against the bottom chord. It's impossible to refill this damper. If you can't refill it, it goes dry, it doesn't serve its purpose, and in fact, the seals dry out and you end up replacing it. These dark photos here are the inside of our New Bay Bridge. So after the bridge was built, it was like, wow, we forgot lighting inside the bridge. We added it in during construction so that we can actually see what is going on inside this bridge. These photos are taken with a camera flash. If I didn't have my flash, this would be like a cave. You wouldn't see anything in there. So, I mean, it's an awareness to think about these things. Someone's gonna have to inspect this and maintain it. So if we're gonna do a big box, put lighting in there. If it's steel, put power in there too, because you're going to need power tools at some point. Okay, so really to summarize all of this, replacements are driven by condition, obviously, but functional and operational needs are driving a lot of bridge replacements. Consider the full life cycle of the bridge, not just the cost at the time you're designing it. Think about these things that are going to happen down the road. Use quality products that have a history of performance. Do not experiment in the wrong places. It can backfire on you pretty easily. Plan for future widenings and rail replacements. Use strategies presented to have future load capacity and maintain high quality welding and concrete curing. And if you can do all of those things, you'll probably squeeze out as much as you can get out of your crossings. And I think in the long run, you would spend less money. And then provide inspection and maintenance access. And that includes vehicle pullouts up on top of bridges too. If you ever inspect bridges and you go park your car in the shoulder and then have to get back into oncoming traffic, you'll know why I say that. That's my ideas for all of you for life extension, so thank you.